let's go through the fundamentals. So practically, each of these chapters have a slideshow. Well, some of them load. The videos will be updated. These are the old videos yet still, but these will be updated. There are also some useful links, and then there's the exercise along with some the useful hints, and then there's the exercise template and a return form. The only way you can actually return these exercises using this form. Okay, anyways, the first fundamentals, let me open this slideshow, and so practically this is the programmable system of 5. So there are different generations of programmable systems. The programmable system of PSoC1 is based on 8-bit MHC core, and then the PSoC3 is 8051 processor, old-fashioned, and then this PSoC5 is actually ARM 32-bit core. I think it was M0 core, but anyways, it's a quite powerful processor already. In addition to that, it has some configurable hardware. So it's basically a single chip system with analog, digital and mixed functions, and not just fixed functions. You can actually program those functions and have different sort of programmable these different setups for a single solution. May have different setups for different needs. So basically this is software configurable, which gives it a lot of flexibility on design. Also the flexible I/O signal routing and programmable interconnects. So those are the different programmable system chip families. So we are using this PSoC5LP. Oh, okay, so it has ARM Cortex M3 core. So PSoC4 has the ARM Cortex M0, but M3 is quite capable processor. The latest addition to the family is the PSoC6, and basically this M4 core with an added Cortex M0 Plus core, which makes it excellent for, say, data intensive the solutions where you need connectivity, like the Bluetooth low energy or Wi-Fi connectivity. Okay, some highlights. So basically we are talking about a real processor, 32 bits, and also 32 input interrupts, which basically can run already, say, real-time operating systems. So it also has a DMA controller, 24-bit fixed point digital filter processor, so you can actually implement digital filters. So thinking of an application where you need to have a data acquisition system, you also can add a digital filter processing on the same chip, one single chip. And then it also has these different building blocks. I will go through those with the tool set later on. And it has 62 capacitive sensors. So basically you can have a capacitive sensing keyboard implemented on single chip processor. And then it also has the analog filters or operational amplifiers, analog to digital the converters or digital to analog converters. It also have a the pre-made solution for up to 736 segment LCD drive for custom displays and packages. We have some packages. Well, anyways, I think it's a modern processor, let's put it this way, plus something else. So practically what we're talking about, what is difference between this processor and some other microcontroller controllers, is that this actually have these building blocks, which means that you don't need that many external devices. This is really a single chip solution. Okay, some words about the architecture. By the way, all of this information I've been just getting from the Cypress web pages. Basically, this on the lowest level is the CPU subsystem, fully digital logic, so it has the CPU core, interrupt controller, and some other controllers there. Digital clocks, then it has the program flash and the static RAM and some other hardware resources. Then it also have this, the next layer is configurable analog and digital blocks. So basically digital block array, it has some fixed functions like UART, PWM, ADC or something like that. Well, actually ADC is reconfigurable. But anyways, it has a set of fixed or universally definable blocks, and then it also have the analog block array, which have a fixed functions for making filters. But then it also okay, what makes it really powerful is the next layer, which is the programmable routing and interconnect, which means that they are already the prototypes, for example, for A to D converters, which are based on both digital and analog blocks. So you don't need to connect these by hand, they are already inside of the tool. So so there's the powerful tools actually gives you access to all of the resources and then some. And in addition, there's also the layer for the ports, up to 8 ports. On the other hand, these devices actually usually have, let's see, on this board what we are using, there is an implementation for port 0, port 2, port 1, port 3, and then port 12 are implemented on the board. So five different ports, which is quite a lot. So 5 times 8 is yeah, it's 40 pins, and it gives you some freedom on also designing your the chip or the program, the PCB layout, so that you can actually connect the pins quite on various ways, so you can minimize the amount of the vias and that kind of things on the printed circuit board. Okay, about the design tools, there's a PSoC creator with support to this this particular the development board we are using. There are the links actually. If you click those, you can access the links, and then the prototyping kit. So fundamentally, everything what you need can be found from the Cypress webpage. Okay, design flow is roughly like this. The first, you would select the target device that fulfills the criteria. On the other hand, when you are doing your first prototype, you would probably use the most capable processor, and then after you have fixed that design, then you can go down and find the cheapest processor which fits the purpose. So yeah, but anyways, you need to select the target device. On the beginning you start with what is available and the highest power I would go. So basically this is why the Cypress is providing this quite capable processor on this cheap 10 USD design kit. Then you start adding the analog digital mixed function blocks. Okay, that's a graphical editor what you will be using. Then you will plan the pinout of the system, then start writing code using API generated automatically. Then you would test the system and debug if needed. Okay, that's the design flow in the principle. Just a couple of reminders. This is as the same design things still apply as in any engineering. You do not start designing the whole thing at the same at once, each single piece of it at the same time. It would make the debugging a nightmare. So first of all, you start with an overall design which basically gives you the framework what should be done. The next you will start the adding the components. So for example, if you need a system that has an analog to digital converter, basically I would start from the analog to digital converter, adding just that one and make sure that it works before going into the next step. Okay, and then on the design flow also it's very important that you keep different versions of the design. So in case you get into the situation that you made a mistake that makes the whole thing more or less a garbage, you would go down on the previous designs until you find a functional version that you can start over, not from the beginning but at the middle. Okay, so that's the design flow for the PSoC5. Okay, that's all for now for this introduction, what we are going to do, or the general idea, what is the PSoC5. There were some links, you feel free to check those, but the next chapter would be showing how this design, what are the required design tools, and how you check that everything works correctly.